Somewhere out there, right now, a galaxy is moving away from us faster than light. We can see it, we've measured it, and it doesn't break a single law of physics. I'm going to show you how that's possible, and in doing that, I'm going to show you something that changes what the word universe actually means. Not philosophically, physically. With numbers you can check. The universe has a hard speed limit, 299,792,458 meters per second, not 1 meter more. And yet thousands of galaxies are violating it, openly, measurably. Right now, as you're sitting there. And this isn't a paradox, it isn't a mistake, and it doesn't mean Einstein was wrong. It means we've been asking the wrong question entirely. The speed limit applies to things moving through space. It says nothing about what space itself is allowed to do. And what space is doing right now in every direction simultaneously is something most people never get told properly. Here's what should bother you. You've been told the universe is 13.8 billion years old. You've been told nothing travels faster than light. Now someone tells you the observable universe is 93 billion light years across, and nobody stops to explain why those three facts, sitting right next to each other, form a contradiction that should make your head come off. They just say it, move on, put it in a textbook. The number is there. The explanation isn't. And most people never notice the gap. I notice it. And once I show you what's actually going on, not the name for it, the actual mechanism, every intuition you have about distance, about motion, about what far away even means, is going to need rebuilding from scratch. Not updated. Rebuilt. Light left a galaxy 13 billion years ago. It traveled at 299,792,458 meters per second, the only speed it knows. It arrived at our telescopes after 13 billion years of uninterrupted travel, so that galaxy is 13 billion light years away. Except it isn't. It's 46 billion light years away right now. Same galaxy, same light. And that single discrepancy, those missing 33 billion light years, is where the entire story lives. So where did those 33 billion light years come from? The answer is not that the galaxy was moving through space while the light traveled. That would still be limited by the speed of light. The answer is that space itself, the distance between us and that galaxy, was growing the entire time the light was in transit. The light was crossing a road that was getting longer underneath it, and it still made it here. But the starting line is now 46 billion light years behind us. This is not intuitive. I know that. Your brain evolved to navigate a savanna, not an expanding universe. So let me give you a picture that actually works. Imagine you're an ant walking across a rubber band. You're moving at a fixed speed, say 1 centimeter per second. The rubber band is being stretched continuously while you walk. You'll still get to the other end eventually, as long as the stretching isn't too fast. But when you arrive, the rubber band is much longer than when you started. The distance you actually crossed, measured on the rubber band itself, is longer than the distance you walked through space. The road grew while you were on it. That's light crossing an expanding universe. The light moves at a fixed speed through space, but space itself is expanding. So the distance the light actually crossed, measured right now, today, is much larger than the distance it traveled. 13 billion years of travel time, 46 billion light years of current distance. Same journey. Both numbers are correct simultaneously. Now here's where it gets genuinely strange. That galaxy, the one 46 billion light years away, is receding from us right now, at a speed faster than light. Not because it's moving through space particularly fast, but because there's so much space between us and it, and all of that space is expanding. And when you add up the expansion of every tiny increment of space across 46 billion light years, the total recession speed exceeds 299,792,458 meters per second. This is allowed. Einstein's speed limit says nothing moves through space faster than light. It says nothing about how fast space itself can expand. There's no speed limit on the expansion of space. None. It can expand at any rate. The universe feels like expanding at, and right now, for galaxies beyond about 14 billion light years away, the expansion is fast enough that those galaxies are receding faster than light. We call that boundary the Hubble radius. Everything beyond roughly 14 billion light years is currently receding from us faster than light. That's not most of the observable universe. That's most of the observable universe. The majority of everything we can see is already moving away from us faster than we could ever chase it, even traveling at the speed of light. and it's getting worse. In 1998, two teams of astronomers, Saul Perlmutter's team and Brian Schmidt's team, were measuring distant supernovae, type Ia supernovae specifically, which are useful because they always explode with roughly the same intrinsic brightness. That makes them cosmic distance markers. You measure how bright they appear, you calculate how far away they must be, and you get a precise distance measurement across billions of light years. What they expected to find was a universe slowing down. After the Big Bang, gravity should be pulling everything back together, gradually decelerating the expansion. The supernovae should appear slightly brighter than a non-decelerating universe would predict, because the universe should have been expanding faster in the past. They found the opposite. The supernovae were dimmer than expected, not brighter, dimmer, which meant they were farther away than a decelerating universe would put them. The expansion of the universe wasn't slowing down, it was speeding up. Something was pushing space apart, and it was getting stronger over time, not weaker. They called it dark energy, which is an honest name in the sense that it admits we have no idea what it is. Dark means we can't see it. Energy means it has effects we can measure. Together, dark energy means something is accelerating the expansion of space, and we don't know what. It makes up about 68% of everything in the universe. We don't know what it is. We've never detected it directly. We've only measured its effect, the accelerating expansion, and worked backwards. This matters for the 93 billion number in a specific way. The universe is 13.8 billion years old. Light has had 13.8 billion years to travel. In a static universe, the observable universe would be a sphere 13.8 billion light-years in radius, 27.6 billion light-years across. In an expanding universe, that radius stretches to about 46 billion light-years, giving us the 93 billion light-year diameter. But because the expansion is accelerating, the boundary of what we can ever observe, the cosmic event horizon, is actually shrinking relative to us. Not the observable universe as it exists now, but the region from which light will ever be able to reach us in the future. Right now, the cosmic event horizon sits at about 16 billion light-years. Any galaxy currently beyond 16 billion light-years is receding fast enough, with acceleration factored in, that light it emits today will never reach us. Ever. The light will spend eternity trying to cross the gap and never make it, because the gap is growing faster than the light can close it. So the observable universe, 93 billion light-years across, is not a permanent feature. It's a snapshot, and it's a snapshot that will, over astronomical timescales, become less and less informative. Galaxies that are currently visible will eventually recede beyond the event horizon. Their light will redshift to infinitely long wavelengths, radio waves, then nothing detectable, and they'll effectively vanish from our sky. In about 150 billion years, a civilization in our galaxy will look out at the night sky and see almost nothing. No other galaxies, no evidence of large-scale structure, no way to know that billions of other galaxies once existed and were observable. They'll look at the universe and think it's just us. They'll be wrong, but they'll have no way to know that. All the evidence will have expanded beyond the horizon. Now I want to go back to something, because I've been using a phrase that deserves more scrutiny. I keep saying the observable universe. What exactly does that mean? And what does it imply about the rest of the universe? The part we can't observe. The observable universe is defined by a simple physical fact. Light has a finite speed, and the universe has a finite age. That means there's a maximum distance from which light could have reached us since the Big Bang. Beyond that distance, light hasn't had time to get here yet. We can't see it, not because it doesn't exist, not because anything is blocking it, simply because light is fast, but not infinitely fast, and the universe is old, but not infinitely old. The boundary of the observable universe, the cosmic microwave background radiation, sitting about 46 billion light-years away in every direction, is literally the edge of our information horizon. It's the most distant thing we can possibly observe, not because the universe ends there, but because that's where our light cone ends. That's as far back in time as we can see, and as far in distance as 13.8 billion years of light travel in an expanding universe can reach. What's beyond that boundary? We don't know. We genuinely don't know. The honest answer, and I prefer honest answers to comfortable ones, is that we have no observational access to anything beyond the cosmic event horizon. We can make theoretical arguments. The simplest assumption is that the universe continues beyond our observable bubble, roughly uniform in its properties, with more galaxies and more space looking much like what we see here. Cosmological models suggest the total universe is at least 250 times larger than the observable universe, meaning at least 23 trillion light-years across. Some inflationary models suggest it's vastly larger than that. Infinite, possibly. But here's the critical distinction. Those are theoretical extrapolations, not measurements. The moment you step outside the observable universe, you've stepped outside the domain of empirical science as we currently practice it. We can't test it, we can't falsify it, we can reason about it, and the reasoning is interesting, but it's not the same as knowing. That boundary, 46 billion light-years, is where physics hands off to speculation. I think it's important to know exactly where that handoff happens. Now, the expansion of space, the cosmic event horizon, galaxies receding faster than light, all of this comes from one equation, not Einstein's field equations directly, though they're the foundation. A simpler derived result, called the Friedmann equation, worked out by Alexander Friedmann in 1922. What it says, in plain language, is this: the expansion rate of the universe at any moment depends on how much stuff, matter, radiation, dark energy is in the universe at that moment. More stuff, different expansion, different kinds of stuff, different expansion histories. In the early universe, radiation dominated, then matter dominated. Now dark energy dominates. Each phase produced a different expansion rate. The universe we observe, 93 billion light-years across, accelerating expansion, cosmic event horizon at 16 billion light-years, is the specific result of those three phases playing out over 13.8 billion years with the specific amounts of matter, radiation, and dark energy our universe happens to contain. Change the amount slightly and you get a different universe. More dark energy and the expansion accelerates faster, possibly fast enough that in a scenario cosmologists call the Big Rip, the expansion eventually tears apart galaxies, then solar systems, then planets, then atoms themselves. Less dark energy and the expansion slows, stops, reverses, the big crunch, everything collapsing back together, exactly the right balance, and you get something close to what we have. We happen to live in a universe where the balance is what it is. We don't know why the constants have the values they have. That's not a cop-out. It's an honest statement of where our understanding currently ends. The Friedmann equation tells us how the universe evolves given its contents. It doesn't tell us why the contents are what they are. That's a different question, and it might be unanswerable. Not because we haven't tried hard enough, but because the answer might require physics we don't have yet, or might genuinely be outside the reach of any physics we could ever construct. I don't know, nobody does. What I do know is this: the 93 billion light-year number is not a mystery or a mistake or a number someone made up. It's the precise measurable consequence of three things happening simultaneously: space expanding since the Big Bang, light traveling at a finite speed through that expanding space, and the expansion itself accelerating due to dark energy. Those three things together, with the specific values our universe has, produce exactly that number. It's derivable, it's checkable, multiple independent lines of evidence, the cosmic microwave background, supernova distances, the large-scale structure of galaxies, the ratio of hydrogen to helium in the universe, all converge on the same picture. The universe is not 93 billion light-years across, despite being only 13.8 billion years old. It's 93 billion light-years across because of how it's been 13.8 billion years old. The age and the size are both consequences of the same underlying physics. They're not in conflict. They're the same story told in two different units. And here's the part that stays with me. Right now, light is leaving galaxies that we will never see. It's already in transit. It's heading toward us at 299,792,458 meters per second, the only speed it knows. And it will never arrive, because the space between us and those galaxies is expanding faster than the light can cross it. That light will travel forever, genuinely forever, without ever reaching a destination. It will cross an expanding void for the entire future history of the universe, getting infinitely redshifted, carrying information about galaxies that no observer will ever receive. There are things happening in this universe right now that are, in principle, permanently unknowable to us. Not because we lack the technology, not because we haven't thought hard enough, but because the geometry of an expanding universe, accelerating under dark energy, draws a hard boundary around what any observer in our position can ever know. That boundary is real, it's measurable, and it sits at 46 billion light years in every direction. Beyond that, we don't know. We can reason, we can model, but we don't know. And I think there's something genuinely worth sitting with in that. Not despair. The universe doesn't owe us complete observational access to itself, but honest recognition that the 93 billion light-year observable universe, vast beyond any meaningful comprehension, is itself just a bubble, a finite region of knowability inside something whose full extent we cannot measure and may never measure. The universe is 93 billion light-years wide, and that's not the end of the story. It's the edge of the part we're allowed to read. So let's come back to where we started. A galaxy moving away from us faster than light. Measurable, observable, not violating a single law of physics. When I first showed you that, it probably felt like a contradiction, something that shouldn't be allowed, a loophole in the rules. Now you know it isn't a loophole at all. It's the rules working exactly as they're supposed to, applied to a universe that is doing something your intuition was never built to handle. Space expands, not into anything, not from anywhere. It just expands, every point getting farther from every other point simultaneously. The way every dot on the surface of an inflating balloon gets farther from every other dot without any single dot being the center. There is no center, there is no edge, there's just more distance between everything, everywhere, all the time. And that changes what distance means. When you say something is 46 billion light years away, you're not saying light took 46 billion years to get here. You're saying that right now, today, if you could freeze the expansion and lay out a ruler, it would read 46 billion light years. The light that brought you that information took 13 billion years to arrive, during which the universe kept expanding, stretching that original distance into something much larger. The distance you measure now and the time the light traveled are both real numbers. They just measure different things. This is not a technicality. It's not a unit conversion. It's a fundamental shift in what the word distance means at cosmological scales. Distance is not a fixed property between 2 points. It's a relationship that changes over time because the space containing those points is dynamic. It stretches, it grows, and right now it's growing faster than it ever has before and accelerating. That's the universe we live in. Now I want to talk about what we actually did to figure all of this out, because I think the method matters as much as the result. We didn't derive the size of the observable universe from pure thought. We didn't get it from philosophy or from authority. We got it the only way you get anything real in physics. We measured things. Specifically, we measured the cosmic microwave background radiation. This is light that was emitted about 380,000 years after the Big Bang, when the universe cooled enough for electrons and protons to combine into hydrogen atoms for the first time, making the universe transparent. Before that moment, the universe was an opaque plasma. Light couldn't travel freely. After that moment, light streamed outward in every direction. That light is still traveling today, 13.8 billion years later, stretched by the expansion of space from visible light down to microwave radiation. It arrives at our detectors from every direction in the sky with almost perfect uniformity, a temperature of 2.725 degrees above absolute zero, with tiny fluctuations of about 1 part in 100,000. Those tiny fluctuations are not noise, they're signal. They're the imprint of quantum fluctuations in the early universe, stretched to cosmic scales by inflation that seeded the formation of every galaxy, every cluster, every filament of large-scale structure we observe today. The pattern of those fluctuations, their angular size, their amplitude, their statistical distribution, encodes the geometry of the universe, its age, its contents, and its expansion history. The Planck satellite measured this pattern with extraordinary precision between 2009 and 2013. The results pinned down the age of the universe at 13.8 billion years, the fraction of ordinary matter at about 5%, dark matter at about 27%, and dark energy at about 68%. From those numbers, combined with the Friedmann equation, you get the 93 billion light-year diameter directly, not as an assumption, as a calculation from measured quantities. Independent confirmation came from supernovae, and from measurements of how galaxies cluster on large scales, and from the ratio of light elements in the universe, hydrogen, helium, lithium, which encodes conditions in the first 3 minutes after the Big Bang. All of these completely different measurements, using completely different physics, pointed to the same universe. Same age, same contents, same expansion history, same size. When independent measurements converge like that, it's not coincidence. It's the universe telling you that your model is right. That convergence is one of the most beautiful things in science. Not beautiful in a poetic sense, beautiful in the sense that it works. The universe is under no obligation to be consistent across different measurement techniques. It just is. And when you find that consistency, when the supernovae agree with the microwave background, agree with the element abundances, agree with the galaxy clustering, you know you've got hold of something real. We have got hold of something real. The universe is 93 billion light years across. The expansion is accelerating. Dark energy is real and dominant, and we don't know what it is. The observable universe is a finite bubble inside something much larger that we cannot observe. Light from galaxies beyond our event horizon is already traveling toward us and will never arrive. These are not speculations. These are the best supported conclusions in modern cosmology, built on decades of precise measurement and multiple independent confirmations. And here's what I want you to take away from all of this, not as a poetic statement, but as a practical one. The universe is not required to fit your intuition. Your intuition evolved on a small rock orbiting an ordinary star in an unremarkable galaxy, calibrated by millions of years of selection pressure to handle objects at human scales, moving at human speeds. It was never designed to handle space expanding faster than light, or light traveling for 13 billion years through a growing universe, or an event horizon that permanently seals off portions of reality from observation. The fact that your intuition struggles with these things is not a failure of intelligence. It's a mismatch of scale. What physics does, what it has always done, at its best, is replace intuition with something more reliable. Not feelings about how things should work, measurements of how things actually work. Models that make precise predictions, predictions that get tested, tests that either confirm the model or force you to build a better one. That process has given us a universe that is 93 billion light years across, 13.8 billion years old, made mostly of things we can't see, expanding at an accelerating rate toward a future in which all other galaxies will eventually vanish beyond an unreachable horizon. It is stranger than anything intuition would have produced. It is also, as far as we can tell, true, and there's one more thing, something that I find genuinely difficult to sit with, and I think you should too. Everything I've described, the observable universe, the 93 billion light years, the cosmic microwave background, the large-scale structure, the billions of galaxies, all of that is the universe as seen from here, from this particular location in space and time. An observer in a galaxy a billion light years away has a different observable universe, overlapping with ours mostly, but with regions we can see that they can't, and regions they can see that we can't. Every point in the universe has its own observable bubble, its own event horizon, its own slice of knowability. There is no view from nowhere. There is no God's eye map of the entire universe. There is only the view from here, constrained by the speed of light and the age of the universe and the acceleration of expansion. Every observation we've ever made, every measurement, every conclusion, all of it comes from inside our particular bubble. We're doing our best to understand something much larger than what we can see, using only the light that has managed to reach us from our one location in our one moment of cosmic history. And we've done remarkably well. 13.8 billion years, 93 billion light years, 68% dark energy, 27% dark matter, 5% everything you've ever seen or touched or measured directly. That's the universe. That's what the light tells us. Beyond the light, we're still working on it.